host a motor driver and a servo connected by a distance sensor. The servo is going to control the action of the gates, which is connected over here, as you can see from the inside. And my astronaut is going to come out from this motor and screw nut mechanism. Let me show you how this is actually working. When the space shuttle is about to land, both my servo and my motor are off. The moment landing happens, the servo will open the gates and my astronaut is slowly coming up. When you view from the other side, this looks like this.
To complete this challenge, all you need to do is shoot a video, upload it on YouTube and share the link in the comment section below. All makers who complete this challenge will be getting a gift coupon and a special prize to make us get the most likes on his or her video. And this time we are giving away any one block from the challenge. I mean anyone. Also guys, remember that the last date to submit a challenge video is 24th of March. To build this project as a friend, like this video, share this video and also subscribe to our channel for new updates. Bye.
So 24th March is the last date and we are not so very much strict, so we can give you one more day time. So I hope we can get more and more submissions from you. It is not necessary to be that you have to purchase a Witblox Kit and make this particular challenge. There is no compulsion like this in our case. If you have developed the same mechanism, do just shoot a video, upload it on YouTube and just share the link with us. You can find us on Google, Amazon, everywhere. Right now, I'm not gloating myself, but we are the #1 robotics kit in India, affiliated by Amazon. Okay, so many of our products are being used in schools and also by individuals, and we have seen how students are making projects on their own. After the talk of guest speaker, I would like you all to just visit our stall over there and see how products are there, and our astronaut Suman sir is also there, so you can have a chat with him. Okay, thank you very much.
Hello wonderful people out there. A very good evening to all. I Ruchira Sawant welcome you all on behalf of Spacegate Mumbai for this talk. It is really appreciable that you all freed up your time and present here on this pleasing evening. And it is enough to understand your passion for space science and learning new things. So in the very beginning, let's have a round of applause for you all. Now after appreciating our enthusiastic audience, we must appreciate them because of whom we all are getting this opportunity to listen our brilliant speaker, Dr. Anita Sengupta. Can you guess who are they? Of course, Spacegate Mumbai, the organization which made this happen. Before we go ahead, let's know who they are and what are they doing exactly. Spacegate is a group of young researchers working in the domain of space science, space technology, astronomy and allied areas. The founders of the group, 3 young researchers, Ankush, Virendra and Chintamani from Mumbai, have always been passionate about space. The motive behind organizing these talks is to inspire the younger generation towards science, technology, engineering and maths. We are also fortunate to have sponsors like Witblox and thankful to them for supporting the event. Look at the red planet at night and who will you think of? Any guess? You may wonder why. It is not too difficult to guess. Our distinguished speaker this evening, Dr. Anita Sengupta. And you may think why we should think of her when we look at Mars. The reason is, when NASA's One-Ton Curiosity rover landed on Mars on August 6, 2013, she had a key role in it. She was a lead system engineer of the NASA team which designed and developed Curiosity's massive revolutionary supersonic parachute, which was largely responsible for the spacecraft's successful touchdown. Curiosity has been making important discoveries in the last 5.5 years. She is a graduate in Aerospace and Mechanical Engineering of the Witblox School of Engineering of the University of Southern California. In her spare time, she is a private pilot, motorcyclist, runner, snowboarder, bicyclist, and science fiction enthusiast. Let's invite her on a dais.
Hello, thanks for coming, everyone. Happy to be here, and I think I was here pretty recently. I think back in November, visiting Mumbai. So I'm going home again to the U.S. tomorrow. I just came from Bangalore. So a little bit of background on me. You just heard it all. All my degrees are in aerospace engineering, bachelor's, master's, PhD. I've been working for about 20 years in aerospace now. 16 of that was with NASA. 3 with Boeing, I guess a little bit more than 20 years, and then a year and a half in the private sector. So my connection to Mumbai is my dad actually got his mechanical engineering degree here at IIT Bombay many, many years ago. And then he moved to the UK and did his PhD where he met my mom. And then we lived in the US for the most part after that. So I've had a really fun career being able to work on a range of different things in the space program. And now I have my venture in the private sector, in the sector of transportation. So my talk today is going to be first starting about stuff here on Earth and how we're improving transportation on Earth, which is my current goal, and then coupling that to how eventually we're going to get people off of the planet to go and live on other worlds. So I won't go too much on my background, but I will say that I've got to work on several really fun missions, and all of these missions are obviously NASA missions, and all of the data from a scientific perspective, and even some of the spacecraft data is available in the public domain if you want to look it up afterwards. So my PhD research was on the development of ion engines, which are a type of plasma propulsion device, and they actually were used on a mission called Dawn. So if you look for dawn.nasa.gov, you can find out about it. And so basically ion engines are very efficient, and they allow you to go to a very distant place from an energy perspective. In this case, Dawn went to the main asteroid belt, and it's visited Vesta and Ceres, one of which is an asteroid, the other of which is a protoplanet. I did that for about 5 years, finished my PhD, and then my management asked me to work on the development of the next rover to the surface of Mars, which was the Curiosity rover, and specifically asked me to lead the parachute development. So I didn't have a background in parachutes, nobody does, but I had a background in aerodynamics. I had taken supersonic aerodynamics, and I was an experimentalist. So when you develop a system like a parachute, you have to do a lot of testing, a lot of analysis, something I wanted to do. I did that for about 5 years. I then did another 2 years working on the development of a Venus lander mission. Sadly, we got to do all the technology development, but we didn't get to fly the mission because NASA didn't pick us. Very sad. I then spent 5 years developing a facility called the Cold Atom Laboratory, which launched in 2018. It's now on board the International Space Station. Its entire purpose is to create a Bose-Einstein condensate. And of course, Bose is a very famous Bengali scientist who developed this type of condensed matter physics with some help from Einstein, but it was primarily all his work. And the really fascinating thing about Bose-Einstein condensate is it's another state of matter that he theorized its existence. He had no way of actually creating it. Move forward a couple of decades, when lasers were invented, another scientist developed a technique called laser cooling. They won the Nobel Prize for it. Another scientist developed a technique to create a Bose-Einstein condensate with laser cooling. They won the Nobel Prize for it. And all of this work was done on the ground, creating the state of matter at really, really cold temperatures. So we decided to create an experiment that we would put on the International Space Station, where you can get to even colder temperatures when you do this kind of experiment in the low-gravity environment. And so it's now working. We're making these condensates on orbit. And the reason why they're important is that the way the state of matter behaves is in a very orderly way. So you basically are creating something which is inherently a superconductor and a superfluid. And so really, really fascinating physics, right? Because typically things tend to disorder. In this case, this thing tends to order. And there's many potential technology applications from being able to use a superconductor or a superfluid. So for an example, a superfluid is you had a cup of superfluid and you spun a spoon around it, it would basically spin around forever because it doesn't have viscous energy losses. So did that for about 5 years. And then I got recruited to leave NASA to join the private sector. And so I actually got recruited to be an executive, a senior vice president at Virgin Hyperloop One. So you've probably all heard about Virgin Hyperloop One in the news because they're interested in building a Hyperloop between Mumbai and Pune. I did that for about a year and a half, working on the development of the system architecture. We developed a test facility, there's some videos on that, and making it safe for eventual human use. That was my role. And then I decided to actually become an entrepreneur and start my own company. So right now, I'm now co-founder and a corporate officer at Aerospace Experience Technologies, which is a vertical takeoff and landing company, and I'll talk a little bit about that as well. But just to give you some background though, sometimes people like to ask me, why did I decide to do what I wanted to do? And ultimately, I'm a huge science fiction fan. I love space exploration. Nothing has fascinated me more since I was a young child. I actually used to watch Star Trek with my dad, who's a huge fan of Star Trek. But I think there's also another reason to do the things that we do, which is that if you take a look at this picture, everybody is very similar to each other, meaning that they had oxygen in their atmosphere, they had water flowing on the surface. But over the course of the past 4.5 billion years, things have changed quite a bit. Venus has a surface temperature of 475 degrees centigrade, that's very, very hot, obviously, and has a surface pressure of 100 atmospheres. Mars, on the other hand, has a surface temperature, in the negative Celsius at best, and has a surface density of 1% of what you have here on Earth. So something happened that caused these planets to change quite differently from each other. And what that means is that climate change is a planetary phenomenon. We can look at our own neighboring planets to see it at this macroscopic scale. So as engineers, as scientists, as science enthusiasts, it's kind of our responsibility to think about how we're impacting our planet and what can we do to change the way we operate, what we study, what we eat, how we get around as a means of protecting our home planet. And I think that's really, really important. But I am not a scientist, I am an engineer, and I like being an engineer, and I think engineering is the best degree that you can get, but that's me, I'm biased. And there's a wonderful quote that's related to that from Theodor von Karman, who is the father of modern aerodynamics, and that is that science is the study of what is, and engineering builds what will be. So basically, engineers take science and math and apply it to create new technology. And with that new technology, hopefully, you can make the world a better place. And I think that's what most of us do on the engineering community in our jobs, is to do that. But I think one of the things that you'll also experience as a young person, as somebody trying to start your own company, as somebody trying to do something which has never been done before, is you'll actually find a lot of people who tell you that can't be done. Right, and that certainly happens in the business sector where you're trying to get money from some venture capitalist and you're like, oh, that seems ridiculous, right? So you're always going to face a certain level of negativity, but I'll give you a wonderful example of why that shouldn't bother you. In the late 1800s, a very famous British physicist named Lord Kelvin, who created the Kelvin scale, for those of you who know a little bit about thermodynamics, he basically said that heavier than air flying machines are impossible. Just a few years later, the Wright brothers demonstrated the first basically lifting body aerodynamic flight. So you can't even listen to somebody who was as smart as Lord Kelvin and make decisions based off of that, right? Because if the Wright brothers had listened, we wouldn't have had flight, and then we wouldn't have the commerce that we have today. So that is something that you have to always keep in mind, is that you got to do it because you think it's the right thing to do. And you should probably do it if it's actually difficult, because it'll be interesting and fun. And then by a show of hands, how many people have seen or read the book The Martian? I recommend it. The book is even better than the movie, but the movie's fun. And the whole purpose here is this guy is stuck on Mars, nobody thinks he's still alive, and the only way he can get through this really difficult situation is to basically use science, the shit out of it is what they say in the movie, to be able to survive. And so it just means that using your brain and using your critical thinking skills, you can almost make anything happen. And where this couples to our society is that I'm a huge fan of science fiction. And the reason why is science fiction creates a different view of the universe the way it could be. There's dystopian science fiction, which is everything's terrible, and then there's utopian science fiction, like Star Trek, where everything's wonderful. So you can actually use that aspect of imagination to be able to create the society that you want to live in. And in this case, you can do it with transportation technologies, as you see in this image, whether it be something in the air, something in the ground, or travel to space. So literally, as an individual, you can contribute in some very impactful way to create the world that you want to see. You don't have to be a bystander. You can actually go off and do it. And where you can take this back from a historical perspective is that technology has changed the world. Go back to 3000 BC, the invention of the wheel. It was actually invented for ceramic purposes, like making pottery, and a little bit later it was used to actually move cargo around. But imagine how that changed society. When you weren't dragging something on the ground, you actually had a wheel-based platform so that you could move goods and services and people. Move forward 1,000 years or so, the Industrial Revolution, or several thousand years, the Industrial Revolution with the invention of the railway network. That actually facilitated the growth of commerce, the growth of economies, the creation of different sectors of economies, and the creation of cities. Now, move forward in another couple of decades, the invention of the personal mobility device, which is the car, that actually allowed far more personal mobility, which of course results in terrible traffic today, and the expansion of cities, right? And once again, it grows the economy because it allows you to do things you couldn't do before. Move forward another couple of decades, you get the invention of the aircraft, and now with jet travel, you can actually connect the entire planet. So you can see how transportation technology, ironically, has changed society, probably more so than anything else, over the course of many, many thousands of years of human society. But what I think you can see, certainly in Mumbai, I just came from Bengaluru, where I live in Los Angeles, transportation also can make your life very miserable because it means you're stuck in traffic. It means if you're trying to transport goods and everybody cares about commerce, they can get stuck at the port, stuck at the airport, cargo on the road, and even more importantly, the amount of pollution that comes as a result of people using vehicles which are operated off of fossil fuels, which actually does damage the planet. So, there's a lot of opportunity there and need, and necessity is the mother of invention, to reinvent transportation. And so the way you think about it is basically with what your customer wants, your customer being all of us in this room, your customer being, the government of Maharashtra, the government of India. They want something which is cost effective, something which has a minimal environmental impact, something which is safe, something which has really fast travel times, you're not stuck in traffic, and something which is ultimately scalable to cities, states, countries, and then much larger land masses over continents. And so there is a lot of work being done in that area, and interestingly enough, a lot of that is happening right here in India, which means it affects your daily lives. And by a show of hands, who has heard of the Hyperloop? Most people, and that makes sense, especially here. And so I like to go back to science fiction. Elon Musk did not invent the Hyperloop. The Hyperloop came about in science fiction. If anyone has ever seen the Jetsons, which was a futuristic society of human beings, I don't know how many hundred years in the future it was, people would travel around in tubes at fast speeds. And so there are other examples of it in science fiction, so certainly it existed in the realm of imagination for a long time. But the reason why it came about is that in the mid-2000s in California, we got an initiative on our ballot, which was a referendum, a yes or no vote, to have built into our budget a California high-speed rail going between Los Angeles and San Francisco. And the measure did pass. It was a lot of money, I think 40 billion, 60 billion US dollars, I don't know what that is in rupees or lots, it's a lot. And as a result, Elon Musk, who's a big, very outspoken technology leader, said, I don't think we should have a high-speed rail. I think we should have something which is a better technology, a more efficient technology, which is a Hyperloop. And so that resulted in him releasing a white paper which talked about what could you do with a Hyperloop, what would it look like, and how would it solve some of society's problems. But what a Hyperloop is, just because I worked on it for a year and a half, I'll talk about it just a little bit, is a magnetically levitating, electrically propelled passenger vehicle in a vacuum tube. And so the reason why it's magnetically levitating is you don't have to have frictional resistance with the wheels and the track. The reason why it's electrically propelled is so that you can use grid-based power, right, which can come from renewables. And the reason why it's in a vacuum tube is that by eliminating air around the vehicle, you eliminate aerodynamic drag, and you can go to really fast speeds at very low energy consumption. And energy goes with the speed squared. So the faster and faster you want to go, because you want to cut your travel time, you would expend more energy in a traditional rail system or a traditional car or a traditional aircraft. In this case, you're more like a spacecraft. So you actually use very little energy, get yourself up to speed, you accelerate, and then you coast the rest of the day, or the rest of the way. And you know what? Oh no, you did open the right one. Okay, I thought I put a video in there. Yeah, it wasn't showing it for some reason. So this gives you a little bit of a view of what this type of system would look like, which is a passenger vehicle inside of a vacuum tube. The primary technology is a linear electric motor. What you see here is a rotational electric motor, which you would have inside of one of these fans, for example. So it's the exact same technology, but instead of a rotational motion, you spread it out and you get a linear motion to be able to go fast and accelerate. And then the whole concept of the vacuum tube is simply using a series of pumps to remove the air from the system, which allows you to go to those fast speeds. This is essentially the system which is being proposed for the route between Mumbai and Pune. And then you can see the magnetic levitation, which gets you off the track, which also helps you go fast and use less energy. And so in terms of where the technology is today, is there are many companies working on the development of the Hyperloop. I worked on one of them, which was version Hyperloop 1, which is the two images you see on the top, where we built a vehicle and we built a test track out in Las Vegas. There were many other companies. I think there's one or two in India, because people contact me all the time on LinkedIn. They make the student teams, but they're working on it. And then there's another company, Hyperloop Transportation Technologies, who's also proposing Hyperloops elsewhere in different states in India. Also working on the development of a test track in France, and the development of a vehicle which will go inside that test track. And so Hyperloop has the ability to let you go really fast at low energy consumption, but because you're going so fast, you actually have to operate the system autonomously, because you can't have a human being in the loop stopping and charting something which is going 1,000 kilometers per hour. That doesn't make sense. And so you do have to have autonomy, but the good news is that the automotive sector is already developing autonomous technologies so that you can have self-driving vehicles. And the complexity of driving a car autonomously is much, much higher than a Hyperloop. And that's because if you're driving a car, you've got people and bicycles and pedestrians that you have to avoid and detect. When you're driving a Hyperloop, you're within a vacuum tube where there are no obstacles. So it becomes a much easier, sort of almost one-dimensional control problem. And what I think is interesting about the transportation sector and the aerospace sector is now there is a lot of private capital out there in India, the United States, and Europe, which means that now other people besides the mega conglomerate corporations can actually create startup technology companies to create these new modes of travel and disrupt the way that people normally travel. And so these images are from different startups TV shows that exist to show you how it is in popular culture. I don't know if that's hit the Indian TV market yet. But what would a Hyperloop look like? It actually looks more like a highway than a train system. All vehicles which are traveling in tubes, bidirectional, one tube goes this way, the other tube goes that way, are traveling at their maximum speed. When they get to a station, they actually exit the Hyperloop highway in an off-ramp to the station, which means that you never have to stop and start on the main line, which allows you to operate more efficiently. And it means every single person who's traveling with you in your little pod is going to your destination. So you don't have to waste as much time, which allows you to be more energy efficient as well. And so where the technology is now, governments around the world are evaluating how a Hyperloop transportation system could be installed in their given municipality, whether it's Mumbai, Pune, whether it's Andhra Pradesh, I think there's one, or whether it's in St. Louis, for example, in the United States. That's currently being looked at by governments, and I see it happening in the next 10 to 15 years is my prediction, where I think we'll probably see one. But that's my personal opinion. You can certainly ask me more questions during the Q&A. So what I am focused on now is the future of air travel. And I will go back and give you another image of the Jetsons where they envision, lo and behold, flying cars. I am a pilot. I fly for fun. Flying is a lot of fun. I would like more people to be able to do it. I don't think it should just be for the people who have a lot of money. And if you do general aviation, small airplanes that I fly, they're actually quite inexpensive, so it can be accessible to regular people. So my company is trying to install urban air mobility systems globally by developing a new type of aircraft technology that I'll show you a video of. There's no audio. I don't think you really need the audio. What you're seeing here is our company is located in Michigan, and we're located in Detroit, which happens to be the automotive sector of the world. And what we're trying to do is design an aircraft which has the ability to take off and land vertically like a helicopter, but has the ability to fly during its cruise like a fixed-wing aircraft. So what you do there is you rotate the wing. So it's called a tilt-wing vertical takeoff and landing aircraft. And so this is a new way of developing an aircraft which has the ability to do this vertical takeoff and landing. And the advantage, of course, is that you can land on the tops of buildings, you can land in parking lots, and you can land in very small airports, which happen to exist all over the United States and all over Europe. And I don't know how many there are in India, but there's probably a bunch as well. And so this is the system that we're building, and we're constantly in the process of designing it and developing our prototypes for it. So sadly, the audio is not working, but I did find this good quote from a famous scientist from India, which is, "You were born with wings, don't crawl, learn to use them and fly," which is what we're trying to do. And so this gives you an idea of what one of these systems would look like, which is a passenger vehicle. It will carry 4 passengers and 1 safety pilot. It could be used by business people going between, buildings on one side of town to the other side of town, or it could be used to make a transit from an urban environment to a suburban environment, or from an urban environment to an airport, such as Mumbai, or a suburban environment to an airport. In terms of why it's important to use eVTOL, E stands for electric. And so instead of using traditional jet fuel, we're going to use batteries. And right now, there doesn't exist commercially available aircraft which operate just on battery power, which means that air travel is significantly contributing to climate change and CO2 production. So we want to actually kickstart an industry which is having electric aircraft for shorter range distances, which will have no emissions, right? So that's kind of the holy grail, is to be able to shift over to an electric aircraft model. At the end of the day, if you can develop this new economy, you will improve upon battery technology such that you can even have longer range vehicle transits. Ours, we're targeting for around 65 miles. Ultimately, we'd like to extend it to a couple of 100 miles, but that requires an improvement in battery technology or a hybrid system. And so you get an idea here of what the airspace looks like in northern Michigan, where there are many, many different airports that you can actually take off and land from to give you this network of travel. In terms of what the aircraft looks like, it looks more like a fixed-wing, high-wing Cessna, which means that it's inherently a glider, so if you happen to lose an engine, you can actually glide down to land, which is very different from a helicopter, where if you lose the engine, you're in trouble. So this type of system is actually inherently safer because of that. To give you a scale of size, the wingspan is about almost 12 meters from tip to tip, and then tip to tail is about 8 meters. To give you an idea of the size. And can't show you any of the nice audio that's coming out. This gives you a view of what the aircraft looks like from the passenger experience perspective. You can see that the cabin can hold 1 safety pilot. We are designing the system to be autonomous, but we also want to be able to carry 4 passengers and a safety pilot, because ultimately the FAA or the Indian equivalent won't allow you to do autonomous flight until it gets certified, which makes sense because it's important for human safety. The other aspect of this type of system is that helicopters are actually very noisy. Our system, because it uses much smaller rotors and has the ability to fly like a fixed-wing aircraft, actually generates much less noise. So you wouldn't have to deal with the noise pollution aspect. And although my emphasis and desire is to carry people, the mission for this aircraft can also carry cargo, humanitarian missions, and reconnaissance. And so this gives you an idea of what the different use cases is like and how you go into the vertical takeoff mode and eventually transition to the fixed-wing aircraft mode.
So where we are is we're doing prototype development, right? So we're all engineers. The most important thing is to build and test as quickly as possible. We built a total of 6 aircraft. They're all subscale, so we can do engineering development. And this is an example of our 3rd scale aircraft that we were showing at the Detroit International Auto Show, actually, in this particular January. So we've flown our aircraft to demonstrate vertical takeoff and landing, transition, and then cruise flight, and then landing back down on the ground again. So the goal here is to use green technologies to basically connect the entire planet. And so the piece which is missing from this right now is electric, low carbon footprint aircraft, which is what we're working on. And that to me is important as a pilot and as a way to help the planet heal. So what comes next in mobility? Well, what comes next in mobility is actually commercial space travel. And what's really interesting is that we are in the precipice of a whole new era of where human beings are going to go next. And that's because there are many companies who are developing commercial launch vehicles to send people into space, not just payloads. And so, of course, Israel has the development of a launch vehicle. I recognize that that's probably a government-funded launch vehicle, but this is going to kickstart an entire space industry in India, in my personal opinion. And the launch vehicle is very powerful, and it's also very cost-effective. So once they start to use it for commercial purposes, I actually think it could be more cost-effective and more utilized than even the SpaceX vehicle is right now. On the US side, commercial space travel is well underway from an engineering development perspective. On the left is Blue Origin, which has created a suborbital launch vehicle to take people into suborbital flights. And Virgin Galactic, which is part of the Virgin Group, has created Spaceship 2, which is going to take people on suborbital flights as well. They've already done demos with their pilots in the loop and some of their own crew as part of it, but eventually they're going to have paying passengers who've already paid, I think, $300,000 for their 6-minute trip into space, or suborbital space in this case, not low Earth orbit. So after that, what everyone is vying for is space travel beyond low Earth orbit, beyond the International Space Station, perhaps to the moon, perhaps to Mars. And on that front, in the United States, we're working on the development of the Orion vehicle. I worked on that for about 2 years, the parachute system for it, which is going to carry 6 astronauts to some destination beyond the International Space Station. And then the commercial equivalent is the SpaceX Dragon capsule, which is being tested right now to send people up to the International Space Station, but I believe has been sized to be able to send people beyond, over to where I think, the next destination is, which is Mars. And so the question is, do you want to live on Mars? I'm going to talk a little bit about that now, and I'll ask you the same question afterwards. By a show of hands, who wants to live on Mars now? Not a lot of people. So unfortunately, the audio doesn't appear to be working. I don't know why. So I'm not going to show the 7 minutes of terror video. I'm looking for anybody who is okay with that, but I can't because the video is not working. Yeah, I don't know why it's not working, but.
We can make the audio work.
What?
Yeah, we can make the audio work.
Oh, how do you do that? Okay, you know how to, but it didn't work for me. Is it muted or something? Yeah. I think it's usually headphones. That's why I saw you do that. That's why I think that's actually the right thing. Yeah, it didn't work. Yeah, it's for whatever reason it's not coming out. We can try, like I'm not even getting any feedback. I can try the external speakers. But it doesn't matter. I'm just going to keep going. It's probably easier. Because I would suggest that if you're interested, you can go to YouTube and look up 7 Minutes of Terror, and then you can see the video which covers our landing team and how we designed the system. But I think there's 2 reasons why we're interested in Mars, though. One is the obvious one, human colonization, right? Where are we going to go next as a species? I actually don't think we should go to the moon first. I think we should go to Mars first, and we can have a discussion about that afterwards. But the real reason is because the technologies that you have to develop to land something on the moon are completely different from the technologies you have to develop to land something on Mars. So if you have resources, money, as a constraint, you probably want to spend them in the most expedient way possible. And I think because of that, we should go to Mars first, because ultimately that's where we want to go, and I think we should focus our resources to develop those technologies. And the reason I say that is because Mars actually isn't that bad of a place to set up a colony. It's much, much worse to go to the moon, actually. The reason for that is because Mars has 1/3 of the gravity of Earth, which means that our bodies won't suffer as much of being in a microgravity environment. It has an atmosphere on the surface. It's very thin. It's CO2, but that CO2 can actually be converted into methane, which provides you rocket fuel to get off the surface, and can also be split up to give you oxygen. Mars also has water in the subsurface, so you need water to be able to live as well. The temperature range, although it does get quite cold, minus 120 degrees Fahrenheit, in the wintertime, in the polar regions, it actually can get comfortable in the summertime in the equatorial regions during the middle of the day. So from a sort of resources perspective, it's actually not so difficult to live on Mars compared to the International Space Station. It's actually much harder. And the day is very similar to the Earth day. So as somebody who travels a lot and suffers from going from different time zones, being able to have a consistent circadian rhythms is actually quite important. But the reason why we have been going to Mars, at least during the course of my career, is to understand how the planet has evolved. And so the picture on the upper left is called Olympus Mons. It is the largest mountain on Mars. It's an extinct volcano, and it's 3 times as high as Mount Everest. So everybody knows how big Mount Everest is up in their minds, right? So imagine that 3 times as high. So what that means is that at some point in Mars's past, it had a very active geological history. But it appears to have stopped, and we don't understand why. The theory as to why it stopped is at some point, many billions of years ago, probably about 4.2 billion years ago, an asteroid came, hit the planet, fractured the core, disrupted the magnetic field. When the magnetic field was disrupted, the atmosphere was stripped away, and then if there was anything living on the surface, it might have died. So that's one theory. It's a pretty good theory, and we have an mission that just landed on Mars in November of 2018 called InSight, which is actually going to make measurements to help test out that hypothesis by looking at whether or not there are Mars quakes, seismic activity, and look at temperature distributions within the planet, digging a little bit deeper into the surface. Another interesting feature, Valles Marineris. This is basically sort of Mars's version of the Grand Canyon, and planetary scientists do believe that the depth of this, which is about 6 times as deep as the Grand Canyon, was formed in part by water flowing on the surface of Mars. But of course, that water from the surface is largely gone today. What we have seen, though, from really high resolution images from a spacecraft called the Mars Reconnaissance Orbiter, that there are still some water flows on the surface of the planet in the form of wet mud or wet soil. And so you can see those in the black streaks coming down this animated GIF on the left, and you can see them as evidenced by past flows on the sides of cliff faces in these 2 images on the right. And so that's really interesting because it means that there is still water frozen in the subsurface, and for a future human colony, you could make use of that water to be able to, drink water, grow plants, wash yourselves, and make oxygen. So it's really, and make hydrogen, which is also another rocket fuel. So the most difficult part about going to Mars, though, is actually landing on Mars. So that happens to be the biggest challenge because you have to dissipate a lot of energy in a really short period of time, and you have to do it all autonomously on the vehicle. You can't have a joystick with someone controlling it. And so we have landed successfully on Mars a total of 8 times. That was all done by the US space program, NASA. The Europeans tried twice and failed, and the Russians tried a bunch of times and also failed. So it happens to be a very difficult thing to do. And the reason why NASA has gotten so good at it is because they've learned from each mission, and they've done incremental improvements from a design perspective, from an engineering technology demonstration perspective in each subsequent mission. We'll be able to build up this database, this knowledge, to be able to be successful. And of course, we just had InSight land in 2018, and Mars 2020 will launch in 2020. And so another element of that incremental improvement is the development of Rover technologies, which is the mobile platform that goes around on the surface and does scientific measurements for you. So you can think of it as a robotic geologist. So in the early 1990s, we launched the Sojourner rover, which was sort of the size of a child's toy truck. Had a solar panel on it, generate power, didn't do much science, it was more technology demonstration. In the early 2000s, we landed the Opportunity and Spirit rover. Spirit died several years ago, Opportunity died only a couple months ago, it's very sad, but it lasted over a decade longer than it was supposed to, so we got a huge return on investment from a scientific perspective. And then, of course, the mission that I worked on was landing the Curiosity rover, which was a very challenging mission from an engineering perspective, because the rover is basically the size of a small car and weighs as much or has the mass of a small car. And so that resulted in many changes to the design of the entry system that I'll talk about a little bit during the course of the presentation to go. But the purpose of the Mars Science Laboratory Curiosity rover mission was basically to determine whether or not Mars could have once supported life and whether or not Mars can still support life. So whether or not the planet was and is habitable. And that is done by making very specific scientific measurements, the most important of which is finding the evidence of organic compounds and making a measurement of what the surface radiation levels are and were. And so the rover has done that actually quite successfully over the course of the past, I guess, oh my gosh, 7 years almost now. But when you design a mission as an engineer, you're working on building the system that gets you there and drives you around. You're not really thinking about the science, but ultimately, the only reason why you're doing it is for the science. And so when you think about where am I going to land the rover, you want to pick a location which is scientifically interesting. So we, the engineering team, worked with the science community to determine where we wanted to land it, and we landed it in a place called Gale Crater that you see on the lower right here, which you can think of as a crater with a mountain in the middle. And the reason why we selected that spot is because of image data that we had from orbit. It looked as though that was the site of an ancient water body. And with an ancient water body, you have the formation of sedimentary rock layers. You have kind of a recorded history in the strata of the rock. And so that's a really good place to go and investigate. And then, of course, you can see how far the Mars Exploration Rover was from Gale Crater. So those two obviously can never meet each other because they're too far away. So that's certainly not the intention. But the way this couples to future human exploration is that it helps you understand the sort of geological diversity of the planet, and that information will help you on a future Mars sample return mission, and also for future human exploration as to where you would want to set up a colony at the end of the day. And so this gives you a three-dimensional view of what Gale Crater looked like, and what you can see is a black ellipse. That was the area that we're targeted to land in with the design of our entry system, and you can see that you have to stay within that ellipse. From a precision perspective, you're a really good dart thrower, you throw it right in the middle. If you're not so good, you hit it out here. And so, obviously, you can't play darts with landing a rover. You have to design the system so that you know it will make it within one of these rings. And so, back in the 1970s, when we landed on Mars, our ability to throw that dart was about 250 kilometers in diameter. Move forward to the Curiosity rover, we had to shrink the ability to throw that dart down to around 20 kilometers in order to be able to land within Gale Crater. So that required us developing very new technologies and control algorithms to ensure that we landed safely. And as you can see, we've gotten better each and every time, and that's how you have that incremental improvement. So the way you get that precision is that the vehicle that contains the rover that you see on the left-hand side there is actually like an aircraft. It actually has a it actually has a lift to drag ratio. So even though it doesn't look like a bird, it is one because it does have the ability to generate lift. And so if you have a lift vector, you can actually modulate that lift vector by rolling or spinning the vehicle and fly yourself down to a place where you want to land, to an extent. That's the way I would describe it. And so this was the first time that we ever did that. And of course, this isn't a human being flying the vehicle. This is the vehicle flying itself because it's making measurements of its position, its altitude, and its speed. And so that's how we were able to improve that landing precision. It was very difficult to do, but it was also it was done successfully. So I think I had a problem with this last time, where it's not, let me go back one. always technical difficulties. Okay, so here's a video that I'll walk you through that shows you what the landing sequence is like for landing on Mars, assuming it works. Yeah, for some reason I'm having difficulties with the video output today, but it's not the end of the world. I can talk you through it in the next slide. I will just have to talk you through it, 'cause it's not showing. So this is a two-dimensional view of what that looks like. So you basically are coming in on an orbital trajectory, which means you have a lot of energy, kinetic energy, you have a lot of speed. And so your job is to basically slow yourself down. So you come in at 20,000 kilometers per hour, that's very, very fast. And the way you slow yourself down actually is with the use of aerodynamic drag. I talked about aerodynamic drag and the concept of the hyperloop here. Aerodynamic drag is your friend in a way. So because the Martian atmosphere has an atmosphere, you can actually use that to slow yourself down. So in case you don't know what aerodynamic drag is, if you're going down the freeway or highway and you put your arm out of it, you feel this force buffeting on your arm, that's aerodynamic drag. And so that is actually a way that you can dissipate your energy to slow yourself down. And so that's a good thing. The problem is, though, is that because you're going so fast, you have tremendous friction with the atmosphere that makes you get really hot. So it actually makes the outside of the vehicle get up to a temperature of around 2,800 degrees centigrade. That's incredibly hot. I think it's like the surface temperature of the sun. So nothing can survive that. So you have to create something called a heat shield that goes in front of the front of your vehicle, which actually absorbs that energy. So the Rover, which is capitalized within it, actually stays a comfortable room temperature. So you use this heat shield to slow yourself down to around 1,500 kilometers per hour, which is roughly 2 times the speed of sound. And at that point, you've hit terminal velocity. You can't go any slower. So then you have to do something to slow yourself down more. So what you do is you deploy a very large parachute, which was my portion of the mission. So a parachute is a really, really large drag-producing device. If this particular one was 21 meters in diameter, so it's pretty large. And so that slows you down from around 1,500 kilometers per hour to around 300 kilometers per hour. Once again, you hit terminal velocity, you can't go any slower, so you actually cut the parachute off, you drop the heat shield, which allows you to expose a radar beneath you, so you can determine what your height above the surface is more accurately, and your speed, horizontal, vertical components. And then you fire retro rockets towards the ground. And I mean, it could have something to do with me showing this in presentation mode. I can try, see if it works. It's a fun video. It's too bad that it's not working for some reason. Oh, let's see if this works. Oh, so it's a problem with, that's the problem. It's something with the conversion error. I'm not quite sure. Probably apologize. I'll just go back to this presentation. You can also find them online if you want to. And so at that point, you're coming down on retro rockets, which then slows you down from around 300 kilometers per hour to around 30 kilometers per hour. And then the Rover is actually lowered on a set of 3 tethers. The engines are still firing, still slowing yourself down. And then eventually the Rover touches the ground, connected to 3 tethers, which you can kind of see illustrated there. The little vehicle on top turns to the side, flies away, and then the Rover has landed on the surface of the planet. So this was the very first time that we developed this landing system, and it was very complicated, but it was needed to be able to land something that heavy and that accurately inside of Gale Crater, and it was successful. And the very first time you ever test the system end to end is actually when you land on Mars. So you can see why it is a very difficult engineering challenge. So to conclude the talk, from the last remaining slides that I have, I want to talk a little bit about the Rover itself and how we develop new technologies for the Rover. So this Rover did not use solar panels. It used a nuclear power source, something called a radioisotope thermoelectric generator, which means you have plutonium-238, which is radioactively decaying, is generating heat. You're then able to convert that heat into electricity. So basically you make your own battery that lasts for many, many decades because the radioactive decay process happens over a really long period of time. And that's good because it gives you a constant source of power all throughout the day and the night, and it gives you more power than you can get with solar panels because Mars is pretty far away from Earth and Mars tends to have dust storms. In terms of what the Rover was intended to do, it was to make scientific measurements, to analyze the composition of the atmosphere, the rocks, and the soil, and to be able to interrogate just below the surface by brushing things and by drilling things and by scooping them. And so that was ultimately the scientific purpose of the Rover. And one of my favorite instruments happens to be a laser instrument, and I like to show this graphic. It did not do this, of course, but the laser was very powerful, which means that if I'm the Rover and I'm firing my laser towards the door, it actually will burn a hole in that door, and it's that heating of the material which actually allows you to determine what the door is made out of. And so it's something called the laser-induced breakdown spectroscopy instrument. So how long does it take to get to Mars? It actually takes, a decent amount of time, 7 to 9 months, which for a little child, that seems like a really long time, right? That's an entire school year, but for an adult, that's not too bad at all. Of course, for any future human mission, you have to be worried that your crewmates are people that you can tolerate for 7 to 9 months. But other than that, it's actually not so difficult of a thing. You can see the entry vehicle containing the rover with the heat shield on the front, sitting under the cruise stage, which took it to Mars, then dropped away, and then entered the atmosphere, and then it launched in November of 2011. And just for analogy, 7 to 9 months is the gestation period of a human sloth to a human baby. So many wonderful things can happen in that short period of time. Now, I hope this video works. It does. So, this was the very first mission where we had a camera on the belly of the rover that was looking down towards the ground as it came in to land on Mars. It was called the MARDI instrument. In addition to providing an amazing view, a bird's eye view of what it looks like to land on Mars, for real, this is what the rover was doing and showing you, it also gave us a set of engineering data that we could use on a future mission to determine how to best land the system in terms of what is my velocity component, how high am I above the surface by actually doing image processing. And so you can see how the field of view is kind of shifting around. The reason for that is the rover is hanging at the bottom of the parachute, so it's kind of oscillating like this. So when you stop seeing it oscillating, that's because the rover has now shifted over to dropping the parachute and is actually descending retropropulsively towards the surface, which starts to happen right about now. And so you can also see that the rover has now, on these descent stage, shifted off to the right. It's getting closer and closer towards the surface. And at some point, roughly, I would say, 22 meters above the surface, you can see the rover's wheels drop into view, and those jets from those engines start to actually intersect with the ground. It's getting closer and closer, and has essentially landed. And the very first thing that the rover was commanded to do, because it had it as its built-in programming after landing, was to send a picture of itself and its landing site. So you can see that here. This was August 12th August 5th of 2012. And you can see here the shadow of the rover looking out towards Mount Sharp. So obviously it had safely landed on the surface. On the right-hand side is a color image of its landing site. And I think something to note is if you've ever spent any time in the desert on Mars, because Mars is largely a desert, looks just like the desert on Earth. So I think that could have been a place in Las Vegas, for example, but it happens to be the surface of Mars. In terms of how we did from a landing accuracy perspective, we designed the system to be able to land within this red ellipse. This little white box here is where we actually did land, which means we did a pretty good job of our engineering calculations of what the atmospheric properties were going to be like, what the winds were going to be like, what the aerodynamic performance of the vehicle was going to be like, and we landed pretty close to the center, right? So that's good. But we had some margin, obviously, in case things went wrong, that would be okay. In terms of where the rover landed, it landed in the upper right-hand side there where the green dot is, and its job actually was to drive towards the base of Mount Sharp, where it has reached to collect science data along the way, with the emphasis of in the vicinity of the lower reaches of Mount Sharp. One of my favorite images from the night was an image of the rover actually suspended under the parachute. And so we were able to take this picture because we have a spacecraft called the Mars Reconnaissance Orbiter, which has higher resolution capability with its camera on board. We were able to position it in its orbit such that it would be able to snap a picture of the descent of the Curiosity rover under the parachute. So that was good for me, since that was the portion I was responsible for. After landing, we do have the ability to communicate with the rover. We communicate with it twice per day, both to give it commands for what it should do that day, as well as to collect the information that it's collected and give it new commands for the next day. But the very first thing that we did actually was to test drive it to make sure that its mobility system did work, drive it in circles, and then go back and forth. And so you can see that in the image here. To give you a little bit of a highlight of some of the scientific findings and capabilities of the rover, that laser instrument that I mentioned before, you can see being demonstrated right here by the rover. So you see that's a rock. When the laser pulse fires, it actually burns a hole in that rock. So you can see that in this animated GIF. And once that happens, a light signal is created, which can then be looked at with a spectrometer, which then tells you what the elemental composition is. And what we can see again and again and again in all the symbols that we've looked at, that we do see the elemental building blocks of life as we know it here on Earth. So another example of an important scientific measurements that are made by the rover, it has a weather station. In the upper right-hand side, you can see the temperature variations during the day, and you can see the pressure variations, and those couple very nicely to the surface radiation levels that we see during the day. And the reason why this is important is it means now we can verify that the atmospheric properties of the Martian atmosphere actually help to attenuate the radiation. And now, even though the radiation levels are still quite high, they're too high for us to be able to tolerate, we now know what we need to do to design to, from an engineering perspective, in terms of amplitude and in terms of frequency content of the radiation, to protect people who would one day live on the surface or live under the surface, right? You could actually use the surface to help attenuate the radiation as well. So that was really important finding, which feeds forward to a future human mission. And of course, the most important measurement, the search for organic molecules, we did indeed confirm the detection of methane, which is a simple organic compound. The reason why that's important is because methane can either come from a biological source or a geological source, both of which are very interesting, because it either means that if it's biological, well, that's obviously interesting. If it's geological, it means that the planet has been recently geologically active. So both of those were very important findings, and also coupled to the InSight mission, which is looking for evidence of current geological activity. So in terms of what is next for us with the exploration of Mars, of course, it's the human exploration of Mars. We did have the very successful InSight landing that happened just this past November. Its landing system was not like the Curiosity system. It was far more simple. It was based on something from many, many years ago, but they didn't have the requirements that we did to land in Gale Crater. They could pretty much land anywhere because they were looking to make a macroscopic measurement of the planet. Nevertheless, every time we're successful, we do learn more about the atmosphere. So what is in the future for us, for Mars exploration? It's largely the development of new technologies that will help us be successful to set up future colonies on the surface of Mars or in other locations in space. So a big one, which couples to what's going on in the private sector, is artificial intelligence. So whenever you have to have human beings in the loop, human beings become fatigued, they can become ill, they might pass out due to, a shortage of oxygen. So if you can have machines make decisions for you on many different things and only leave up really kind of key scientific making decisions to the human beings, that actually makes a lot of sense. And in terms of what's being developed from a robotics technology perspective at NASA, is we do have Robonaut, and so Robonaut is designed to be able to do a lot of the menial tasks and make decisions so that we can take off less of the work from astronauts that exist. Another really important one is the growing of food. It is not feasible or possible for us to bring all the food with us there. I think that's kind of silly. It's sort of like, every time you go, do you live in your house and drive out the road back and forth in a motorhome? No, you have a home, you grow food in the home. So you don't want to have to transport large quantity of food from Earth to Mars. So you want to be able to grow food when you get there. And so you don't have to grow it on the surface. You can have subterranean habitats. You can feed in light using fiber optics. And you can use very special plants called extremophiles, which need very little oxygen, primarily CO2, and actually generate oxygen as a result of photosynthesis. And in terms of what's being done now, we actually have made work in this area in terms of growing food in space. On the International Space Station, there's an experiment called the Veggie experiment, and within this facility, the astronauts on the space station have grown lettuces, actually. So they've shown the growth of plants in a microgravity environment. The bad news is that plants do not grow well in a microgravity environment because they need that forcing function. They need gravity and they need light to figure out how to grow. In a microgravity environment, they kind of just grow all over the place and they're not very efficient. The good news is that on Mars, you actually do have gravity, so the plants will be able to grow better. But it's really important to learn about how they do these things in space so that we can figure out how we do them before we get to the surface of Mars. And then another really important part, which couples to the earlier discussion of being green, is on Mars, being green is essential for survival. And the other way of referring to being green is in situ resource utilization, ISRU, as we like to say for short. What that means is how can you use the resources already available to you on Mars to generate power, to protect yourself from radiation, to be able to collect water, to be able to make rocket fuel, methane, and also to be able to grow your own food. And in each one of these areas, there are engineering technologies that have to be developed or further developed or invented to be able to facilitate a future human habitation on the surface of the planet. Power is an obvious one. If you have a big base, you can actually have a huge solar panel farm and use that as a means of generating power, right? Because you can ultimately have people putting out larger and larger solar arrays. Radiation protection is also a pretty, not a simple one, but there's a way that you can use the Martian soil, put them into bags, create bricks, make habitats, or simply dig yourself beneath the surface of the planet in a subterranean habitat to protect yourself from radiation that is inherent both from solar radiation from our sun as well as galactic cosmic rays coming from deep in outer space. Even with that, of course, though, you do have to worry about the interplanetary cruise between Earth and Mars. You do need radiation protection there as well. That happens to be the driving radiation case. That also requires new technology development. But that's not specific to the surface of Mars. We do know that water is frozen in the subsurface, which means that water can be tapped into for use in a future human colony for washing, eating, growing plants, making oxygen, and same thing with methane. And so these are all areas that I think can and should be actively worked on, both by government space agencies as well as private companies. Now, can you imagine going all the way to Mars and not being able to drive around? That would be pretty terrible. So you also need surface mobility options for people who would live there. Now, of course, those surface mobility options would have to be pressurized, right, because you would have to be living inside of there, and they would have to be rechargeable at your home station. And so I think there were some examples of that in the movie The Martian. Good news, that's also being worked on. So this is an example of a surface mobility vehicle from a drivetrain perspective. It's an electric vehicle that's being developed at NASA. And this was us messing around in it when we were visiting the facility where it was being tested. So basically, the future of mobility, the future of humanity, probably is, perhaps not in our lifetimes, but probably in our children's or our grandchildren's lifetimes, are colonies on other worlds. And I personally hope and think it should be Mars. I do think that within our lifetimes, however, that we will see the first people on Mars as individuals as opposed to a colony. And so there is a lot of work to be done in the development of life support systems and habitats and understanding how human beings are going to interact in these long duration stays on the surface of another world. And so I think what's so amazing about space exploration in general is that it actually creates a level of enthusiasm in young people to become scientists and become engineers. I certainly became one because of the space program. Pretty much all of my colleagues I know have become engineers because of the space program. And all the data that we collect is always returned to Earth, available to the public for everyone to view and analyze. And so I think that space exploration is so important to the motivation of young people. It is important to our future. The follow-on technologies from the space program, and there's just so many that impact our society and make it a better place and create jobs and create new economies. I mean, look at the mobile communications sector, for example. And so I think that's really important. So I think I'll spend the rest of the time taking questions, but I am pretty active on social media, so you can always follow up and ask me questions on my Twitter account or on my Facebook page. So thank you. I've talked for a long time, so you must have some. Which one first? You decide. By Israel. So I haven't actually followed their mission, but I don't view space exploration as like this country versus that country versus this space agency versus that space agency. I view it as sort of like a global thing. So I'm always super excited and super happy when a country or space agency is successful. So, which is awesome. So yeah, actually that's not true. I did meet the guy at a conference in September. Yes, I did meet the person. So I didn't actually realize it had already gotten that close to being done. But I think it's fantastic. And so I think that the shift to commercial space exploration, the shift to the use of private capital to fund these developments is really important and probably what is required to make something as tremendous as a future human colony become possible. Because when you spend large quantities of money, you have to have a justification for it. So if there is a business case for these things, whether it's the selling of property on the moon, I don't know, or just the fact that people are going to want to expand just like they expanded to other continents on our planet, I think it's a great thing. So I wish them success. And this lady up front had go first. But. I think it's because politicians aren't scientists or engineers. I think that's the reason. And I actually tweeted about this last week, and I described the fact that somebody put up a graphic of like the path to the moon. That exact same graphic had a red background on it a couple of years ago, which was the path to Mars. So the analogy I gave is that I have a cat, and when I leave the back door of my house open, the cat sits at the threshold, goes outside, goes inside, goes outside, goes inside, can't make up its mind. So I think, unfortunately, when decisions are made by purely for political reasons, you don't get the most efficient solution. And what happens, and I actually tweeted about this, is that you waste resources. So instead of burning down technological risk and actually like, I'm solving the radiation shield, I'm solving the engine technology, I'm solving the life support system, you make no progress on anything. You just waste the taxpayers' money. So I think it's terribly irresponsible that we keep shifting back and forth, but I think it's because there isn't a continuity and a long-term vision, and it changes with every election cycle, unfortunately. In the US, it's with every presidential change-out. I don't know what it is in India. I assume it's the same thing with the prime minister. So I think it's unfortunate, and maybe the only way that you could change that is that if it was part of the public discourse that says, no, you know what, no, we want to go to the moon, right, or we want to go to Mars, which is what I want to do, then maybe that could somehow impact the way these decisions are made by the next administration. But I've just seen it in my career. I've seen it 3 times now, and it's so frustrating because there's so much waste. And then another example would be in the human space program. In the, I think it was probably the early 2000s, the Constellation program came about, and they spent all this money developing a launch vehicle. And all of that just stopped. And now what are they doing? They're developing a launch vehicle again. So there's no continuity, there's no leveraging from what has been done before. And I think that's unfortunate, because ultimately what it does is it actually keeps us making us 10 years away from an eventual goal, but you're always 10 years away. So I think that's sad. So I would say public engagement to help drive how these decisions are made might be a way of dealing with it, which is actually largely why I talk publicly, is that I actually think it is a bad thing that we're moving back and forth, because we're wasting money and we're wasting time. So, but it is sad, but I recognize it, and I wish I could do something about it. But maybe they'll make me an NASA administrator. Yes.
Given that hyperloop is still there, I would like you to elaborate on a couple of things like, cost effectiveness, right of way, and safety to human beings. One of the debates going on in India is, so we need to spend $1 trillion on the Ahmedabad high-speed train, and we put that same money in hyperloop. Could you take us through a few things that, and a timeline that you see?
You know what's funny though is that debate about high-speed rail or hyperloop exists here. It exists for some people. It is in California. It exists in England. In England, they're building high-speed rail. So the argument is there's 2 arguments. One is that governments have responsibility to make progress and to give some other people a service. And so if the government was to invest in a technology which somebody who makes the decision views as too high a risk, then perhaps that's irresponsible, and it's better for them to go with the technology which somebody has assessed as being lower risk, right? So that's the reason why you would pick the lower risk solution. But if you're trying to do a long-term plan, then you need to engage the public and say, yeah, there may be some cost risk up front. It's not that it won't work, it will all work, right? There may be some cost risk up front that we'll have to pay for or a lot for, so that we can actually implement a better solution in the long term, which is more scalable, which is more environmentally friendly. But once again, it comes back to politics and people having the vision and even sort of like the personal strength to take a little bit of flack, right? To say that, well, maybe this won't go right, but in the long term, it's going to go really well. And the best example I can give you, at least in the U.S., is John F. Kennedy, right? John F. Kennedy, almost single-handedly created, the lunar program, right? Where everything leading up to Apollo, because he had this personal vision, he had this personal strength, and he wanted it to happen, and it was really important to him as a person. So sadly, sometimes I think it takes that kind of very unique individual to make that happen, but I don't think Hyperloop technology is actually a compilation of the technologies that already exist. Maglev trains already exist. Vacuum systems at that level already exist. They're off-the-shelf pumps. The ability to control a maglev train already exists. So there's nothing inherently about a Hyperloop, in my opinion, which makes it in any way, shape, or form a technological risk or a human. Well, so I think the difference between a maglev train and a Hyperloop passenger car is that a maglev train doesn't have to have a pressurized passenger car. A Hyperloop is basically, passenger car is like an airplane without wings. So even that exists, right, in terms of having something which has to be at high altitude. So like a Hyperloop is something like 100,000 feet altitude is what the pressure level is. So even that is not something which hasn't been done before. It's putting it together in a different way, right? It's a different system integration. But there's nothing about the technology which is inherently, it's all an easy engineering problem to solve, in my personal opinion. What is challenging, however, is because it's a new form of transportation, there may not be an existing regulatory body, there isn't an existing regulatory body, and then as a result, there aren't engineering standards which exist that you simply say, I met this standard, I met this standard, I met this standard, I'm good to go. That is regulatory risk, but that's different from engineering risk. Once again, that's a political problem.
So there's no commercial service in the near future in the US? Maybe cities, is there any?
Not that I'm aware of. There are a lot of studies underway on how you could implement something like that. Like there was a report that came out a couple of months ago in St. Louis, between St. Louis and Kansas City, where they're interested in building one. So I think it just takes a little bit of time for governments to take a look at what's needed. And then how to implement, and there's this whole procurement process, right, you have to go through. So it just takes time to get from that point of doing that first study. But as an engineer, I can simply say that the technology is something which can be implemented pretty soon.
I think Abu Dhabi's divided is.
Oh, okay.
Really need to send the units to Mars. I mean, can't we do it with Rover? Since we have such technological advances of robotics right now, we really need to put humans into the 11-month time period where you are likely to have a little process for that.
So it's a good point, and I think the question of need is not something that can be quantified. So I don't believe it's there just to do it and we never go back again. I actually believe in setting up an architecture where you're starting to set up actual infrastructure of people eventually living there permanently. So I don't view it, I don't mean permanently as in a one-way journey, but as in this is a new place to live, right? Go get your plot on Mars. So and in order to justify that, you need to justify it from a business perspective, right? There's some kind of return on investment from having done that, whether it's, I don't know. It's sort of like our society will change to facilitate that. But you don't need to have humans for scientific reasons, right? You can collect really incredibly useful data doing it robotically, which is what we've done with the robotic space program for the past 20 years. But if you eventually believe that as a species we are going to live somewhere else, I actually think, and we want the government to be a part of that, like that whole investment, just because somebody has to kickstart it, that's the reason why you would do it. But you don't need to do it for science purposes. Yeah, you can do it robotically. And another argument that could be made is that, even if people want to go, what about using VR, right? So if you have the images coming back from the rover, yes, there's a time delay. But if you can just watch it real time, then you even get that experience. But I think the justification for climbing a mountain is because it's there, or the justification for going to new places and exploring, new cities and new geological sites. You do it because we're human beings and we're interested, we want to explore. So I think it's just our inherent need to explore, which makes me and others, and probably society at large, want to go and live somewhere else off-world. So. So I did actually meet a lady this past week in Paris at a futurism conference I was at, who was specifically working on swarm intelligence, and it was very bizarre because it seems as though there has to be sort of an AI element to how they learn from each other to make the thing happen. So to me, it didn't really seem that prescriptive as to how you would make it happen. So I'm not sure. It's not my area of expertise, but I think people who work on that look at analogs in, animals. So like she was looking at swarms of bees. She was looking at flocks of birds and how basically they are greater than the sum of their parts in terms of their ability to survive, in terms of their ability to get from point A to B, complete their mission. So. I don't know how you directly couple that to a discrete solution. That's what freaks me out, because as an engineer, it's like, we gotta have a solution, like to work towards something. So there did seem to be a little bit of randomness to that, which is odd. So that I don't know enough about, but there are people who are actively working it, and I know that it has been used successfully in some instances of like security screening and stuff like that, where they're able to do AI, I guess not really swarm behavior, but to help you be more efficient for things where you have random number of generation and stuff like that. But it's not my area of expertise, unfortunately. So I was really interested in what she was talking about, because I didn't know a lot about it. So maybe in a couple of years I'll know more. There's another lady here. Yes, and I agree, and I think ultimately I am fascinated by exploration. I love to go and visit new places and try new foods and see new archaeology, just because it's so cool and so exciting. So I think that's kind of what makes human beings so unique from other animals here on Earth. It's just our innate desire to understand the unknown, and I honestly feel like that's what drives us to do what we do, right? Because why on earth do I need to understand whether or not Enceladus has organic compounds in its plume of particles? Because I think it's awesome, and I do want to know, right? And I want to understand how that planet evolved versus our planet. But there isn't, it's more of a gut emotional thing than anything else, I would say. Absolutely, and I think a great analogy of that, because it was related to my cold out laboratory experiment, was that when the people were working on the development of the first coherent beam of photons, which is a laser, people said, what on earth are you going to use that for? And a laser is used for everything, right? So fundamental research, fundamental scientific research, development of technologies for space program have applications here at home, from materials to fuels to solar cells to telecommunications to miniaturization of electronics to software development. I mean, the list goes on and on and on. You can only see the benefits of the space program because of that spin-off, because of the inability to predict the future, because that perhaps is the swarm aspect of it, swarm science. Well, I personally don't believe that, because sometimes when I look at the clouds, I see like a cat. So I don't. I think it's just an optical illusion type of thing. And I will say, to take that a little bit further, the spacecraft, one of the spacecraft that we have orbiting Mars Reconnaissance Orbiter, has the HiRISE instrument, which has the ability to detect the resolution of things, to the order of meters, which means that if there was some kind of civilization or additional evidence of civilization, you see far more that one feature. So it's not statistically significant, right? Because if there was evidence of anything, we would see it. Even if, so we just don't. So for that reason, I don't think so. Gentleman here, the lady behind. You're the gentleman.
So you said that you worked on ion propulsion for 5 years. I would like to ask, in your opinion, which futuristic space propulsion would be feasible in next 150 years?
So ion propulsion is already used. So my very first job, actually, my second job at Boeing, was developing ion engines for the Hughes 702 communication satellite. So ion engines have been flying around in geostationary orbit to do orbit raising and orbit maintenance for many, many years. They were developed, I think, in the 1950s by the Russians, and then some people working in the US. The problem in ion engines and Hall thrusters, they all work incredibly well. They're so efficient, and the reason for that is that chemical thrusters are limited to the chemical energy of that chemical reaction. You can never get beyond that, which means that you have to carry more fuel if you want to go faster. Electric thrusters are only limited by the amount of electrical energy you can put in. And then that just gets directly converted into kinetic energy and then momentum transfer. And so what limits you in the use of ion propulsion is the absence of a power source as you get further away from the sun. So right now, as you get further away from the sun, the radiation drops off 1 over r squared, and they get a reduction in amount of energy available. So ultimately, you would love to use ion engines to take you to Neptune and Uranus and Pluto, but there's no power source because you're getting further away from the sun. So somebody has to develop a space-based, basically nuclear reactor technology to facilitate nuclear electric propulsion is what it's called. So back during my thesis days, we actually developed a thruster which was at that scale, using ground-based power to demonstrate how to design and how it works. We built with it, like it's sitting there. It was actually in James Cameron's video back in probably 2004. He came out with an IMAX movie where it's like, for some reason, he showed a picture of our engines that we developed. So that, once again, technology exists, we built it, but we don't have that power source. And because nuclear power is obviously, controversial, requires a lot of money, requires a fuel source, which doesn't happen every day, like people aren't going around and enriching fuel every day. That's the thing, which is the temple, is the power source, not the engine technology. I think that's kind of the ironic aspect. So we were talking about this last night at dinner, actually, but if somebody can come up, with antimatter, right, as a means of providing a power source instead of nuclear fuel, maybe that's a way around it. So there's all these like tertiary subsystems that have to be developed, and then you have to be able to have a containment thing that would go around the antimatter. That has to be done. So the sad thing is, like, from an engine technology, we're ready to go, but we can't because we don't have the power. Somebody needs to figure that out. And then lady behind you. So I'm not as familiar with space elevators, but I am very familiar with rail guns, which they're not quite the same thing, but it's like using electricity to take you up to altitude. So I think there's probably a lot to be said about a railgun technology, right, where you can impart a lot of your kinetic energy to escape the potential energy well using ground-based power. I think that would be awesome if we have something like that, because then you don't have to release as many carbon emissions. So I just don't know about enough about the space elevator to comment, but if we can get around the gravity well problem by using ground-based power and we can beam it to the vehicle, we should do that, right? Because otherwise, every time we have a rocket launch, we're actually emitting, fossil fuels and then greenhouse gases, which is a terrible thing. So I wish somebody would start working a little bit more on that, which maybe all of us can take that as a motivation for something to work on, so that we can really, to have a spacefaring society, we don't want to kill our planet in the process. That would be terrible. So I will look up on that thing, because that's interesting. Or you can send me a link. Okay, this gentleman.
If you can just give a couple of differences between the parachute used in Earth and parachute designed for Rover.
Oh yeah, so the primary difference is that you have to deploy a parachute on Mars supersonically, just because you need altitude margin before you smack into the ground, and because the air is so thin. So because of that, it experiences these incredible aerodynamic instabilities, which require it to be very, very strong. But with any spacecraft mission, you're very constrained to how much mass you can bring with you, so it has to be very, very light. So it has to be very, very strong, very, very light. That's a very difficult combination. So parachutes for Mars uses are typically made out of very modern materials. They're made out of very sophisticated nylons and Kevlars, which are high strength to weight materials, which makes them more expensive than parachute that you would use for a sport application. For a sport application or for a re-entry system for Earth, they're deployed subsonically, which means they don't have to worry about the supersonic aerodynamic instability, which means that the load on it relative is a lot lower, which means they don't have to be as strong, and they're more likely to be successful. And then, of course, the huge difference is that for a parachute on Earth, you can actually test it ahead of time, because you can match your conditions. For a parachute on Mars, you can't. So all you can do, what we did was we built little subscale versions of the parachute, put them in a supersonic wind tunnel, matched the conditions on Mars, did the right aerodynamic and dynamic scaling to get what we thought was the correct geometry, not geometry, but performance out of the chute, and then see how much of a load factor it saw, and then build the full-scale chute to be able to survive that. So but it was a research project, actually, so it was fun. Yeah. Yes, I think it should be exactly the same. There shouldn't be any differences. Say again? We're going to use a Skype, but I think they are going to use something to do with terrain relative navigation. I did take that slide out. So part of the Marty camera that was looking down towards the ground taking the pictures, that allows you to do terrain relative navigation. So on board in the computer, it has a map of what the surface looks like with different features. When the camera is taking those pictures, it does a detection of when it sees one of those features, and that gives you a better understanding of where you are relative to where you need to go. So that helps you be more precise. It allows you to either be more precise or carry less fuel, or a combination of those two things. So that was a technology demonstration, which then feeds forward into a Mars mission, which also feeds forward to a future, hopefully, Europa lander 20 years from now, or 30, I don't know. Gentleman here.
When you said about the nuclear power vehicles, do they not have any
So the interesting thing is that plutonium-238 is not a very toxic reaction. So you can actually handle plutonium, not with your bare hands, but with something around it. So it has a very long half-life, which means that the energy that's putting out is quite low. So you don't get X-rays generated or anything like that. So it's not dangerous in that way. That being said, you have to, if you need a lot of fuel, and I'm not a nuclear physicist, but I do know if you need a lot of plutonium-238 and you package it too tightly, you can have situations where you get neutron interaction and things can go like supercritical, but you obviously would design it so it doesn't do that. But in general, that source of nuclear material, from a proximity perspective, doesn't have like X-rays or gamma rays. The concern, of course, is if you have nuclear material and you have some kind of, I don't know, explosion, you want to be able to contain it because you don't want particulates to get out, right? And so aspirating and stuff like that isn't good. So I'm not saying it's not something you would want to be exposed to, but it's not in the same way as nuclear materials that they use for missile purposes. They have much larger energy expenditure, energy output, and a shorter half-life. This lady here. Oh, okay, last question. Sorry. Oh, so I mean, of course I would like to, but I think, and I hope I get to one day, but the idea of making your whole life about that one thing, right? Imagine if my journey had been about just that. I wouldn't have been able to do all the other fun things. If I guess to be part of my journey as a commercial astronaut, like buying a ticket on Virgin Galactic or something, or on SpaceX or Blue Origin, I think what's going to change in the near future for all of us is that almost anybody is going to be able to go into suborbital space. There's a certain cost associated, like you'll have to mortgage your house. So is that worth it? I don't know. I probably wouldn't get a second mortgage in my house to go on that journey, but I think now it's becoming actually realistic for regular people to be able to do it. So it's not as much of a thing where back in the day in the Apollo era, nobody could do it. Of course, there's also the, sex-based discrimination where women couldn't go at all. So no, I think it'd be awesome, it'd be a lot of fun. I'd like to go to Mars. But I do think as you get older, you stop thinking about yourself and all of your individual needs, and you start to think about how can I impact society in a bit bigger way. And I think my choices of how I've organized my career have let me do that. And now being in the private sector and having a company, being an entrepreneur, I think I can do that even more because now I can speak whenever I want to, travel whenever I want to, as opposed to what my boss says, because I'm my own boss. I guess I'm supposed to stop talking now. One thing I thought would be fun though is if we took like a picture as a group before everybody left. Like I could stand there, then somebody could take the picture from there. But I don't know when you want to do that. But just before everybody left, that'd be fun. Okay. I'll let you guys decide. You're my boss right now.
Hi, I'm Dr. Anita Sengupta, and as we are space geeks, we are also doing faculty research. So here I have something to share with you that we are working with a company in Mumbai called Stable, which actually supplies product to ship and cruises where it nullifies the motion of ships. But then here we have come across a solution. So what if you go on a ship and you are observing the star? So the star will of course will move around because of the ship's motion. So here we have the R&D development that Stable in Norway, where we will come up with a product which can modify the motion of the ship. You can have the stable observation of stars and deep sky objects.
This is when we came across some problem like this when we went on a Mumbai Goa cruise in Anita. We did a sky observation program. We came across this problem and we actually found this problem.
So we now represent Stable in India for the astronomy applications.
So I have been given this task of producing both of tasks. Firstly, grateful thanks to Anita for taking us to the red planet and to the Earth planet. So I will invite SpaceGate team to hand over a vote of gratitude.
Image taken of Supersonic by Rover. We keep going to the locations to capture night sky. So since you are Mumbai, so this is taken from the AP of India. It's open last month.